Good afternoon to one and all. Myself Sayanil Ghosh, student of Department of Chemistry, Bolpur College. Today I am presenting my dissertation topic titled The Crystal Field Theory. It all started with the Warner's coordination theory in 1893, which was the first attempt to explain the bonding in coordination compounds. This theory was put forward even before the discovery of electron by J.J. Thomson. After 20 years of his work, in 1913 he won the Nobel Prize, which happens to be the same year in which Kavi Guru Rabindranath Tagore became the first Indian citizen to win the Nobel Prize because of his beautiful translation of Gitanjali in English, which goes by the name Song Offerings. Warner's theory has some limitation. The bonding patterns was not clearly understood. After his work, scientists proposed many beautiful theories to explain the bonding pattern and physiochemical aspects. Some impactful theories were the valence bond theory, the crystal field theory, which is the main topic for my presentation, and the ligand field theory, LFT, or the molecular orbital theory, MOT. The simplest theory to describe the bonding pattern in complex compounds is the valence bond theory, proposed by Sir Linus Carl Pauling, who was awarded the Nobel Prize in Chemistry because of this theory. This theory assumes the formation of a coordinate bond arising due to donation of electron from ligand orbital to metal. Here I have shown a D2sp3 hybridized octahedral complex compound. The structure is according to VBT. Now, here I have two different complex compounds with different hybridization, but they are identical from the aspect of formula. The reason behind this difference is not clearly explained by VBT, and this is the main discrepancy which triggers the need for a better theory to describe the bonding pattern in complex compounds. Some other limitations of VBTs were: to explain these properties, Hans Bethe and John Hasbrouck van Vleck independently come up with a new theory which is known as the crystal field theory. This theory is based on some basic assumptions or postulates. The ligands are considered to be a point charge or point dipole. In a particular geometry, the ligand approaches towards the metal atom along some preferred direction, which we will see in the next slides. And most importantly, this theory considers the metal ligand interaction to be purely electrostatic with no orbital overlap. And lastly, the splitting of 5 degenerate d orbitals. In an octahedral geometry, the metal atom occupies the center of the octahedron, and the 6 ligands approaches the metal ion along all the axes. Now, if we look at the orientation of d orbital of metal ions, we can see the Eg set of orbital, which is dx square minus y square and dz square, will face the ligand head on, and the T2g set of orbital, which is dxy, xz and yz, have their lobes in between ligand. As a result, the Eg set of orbital is destabilized and get higher in energy, and T2g set of orbital is stabilized and lowered in energy, and that's how we get the splitting in an octahedral geometry. The energy difference between T2g and Eg level is known as the crystal field splitting parameter or crystal field strength, expressed as del O or 10 dq. Here I have two chromium 3+ complexes, a D3 system with different crystal field strengths expressed in terms of wave number. With the help of electronic configuration, we can also calculate the crystal field stabilization energy shown in this slide. Now, for a tetrahedral geometry, it is considered the metal will situate at the center of the cube and the ligands will occupy the alternate corners. Here the T2 set of orbital, which is dxy, xz, yz, make an angle of 35 degrees 16 minutes with the ligands, and the E set of orbital, the dx square minus y square and dz square, make an angle of 54 degrees 44 minutes. As a result, the E set of orbital is stabilized and decreased in energy, and T2 set of orbital is destabilized and increased in energy, and that's how we get the splitting in a tetrahedral geometry. The splitting in different geometries is shown in this slide. Now, the spin state of a complex depends on the crystal field strength, which is represented as del O, and the pairing energy P, defined as the energy needed to pair up two electrons with opposite spin. Here I am taking two D6 configuration with different del O values. First one is higher than pairing energy and second one is lower than pairing energy. We can arrange the first 3 electron in T2G level for both these cases. But in the first one, the higher del 0 will tend to initiate spin pairing, and we get the electronic distribution which does not take place according to Hund's rule. But in case of the right one, the electron will enter the T2G and EG level according to Hund's rule, and that is how the high spin state and low spin state is generated in an octahedral geometry. Most of the tetrahedral field is not strong enough to initiate spin pairing. As a result, low spin tetrahedral complex doesn't exist. The crystal field strength delta T is lower because of having just only 4 ligands compared to octahedral geometry, and not for having any head-on interaction with the ligand. As a result, the delta T is 4/9 times weaker as compared to the delta O. Here I have shown D4, D5 and D6 configuration in a tetrahedral geometry. The CFSC calculation is also shown in respect to delta T and delta O. For the same metal ion in and same geometry, the magnitude of crystal field strength varies from ligand to ligand. Some common ligands can be arranged as following in an increasing order of their splitting power. This arrangement is known as the spectrochemical series of ligand. The order we obtain will remain practically constant for different metal atoms or ions. Starting from pyridine, we have this strong field ligand which will initiate spin pairing to give a low spin complex. The ligands I have shown in blue color are the pi donor ligands, the yellow ones are the sigma donor, and lastly the purple ones are the pi acceptor ligands. This classification of ligand has no contribution in CFT, as this theory doesn't consider any metal ligand orbital overlap. CFT is proved to explain some phenomena which the previous theories failed to explain. For example, CFT satisfactorily explains the variation in ionic radius for bivalent metal atoms in metal oxides. If we go along the transition metal series from left to right in periodic table, it is expected that the radius of an ion or radius of a metal ligand, the metal ligand distance must gradually decrease with increase in the effective nuclear charge. Because of the increase in the effective nuclear charge, it is observed that the calcium 2+, manganese 2+, and Zn 2+ follow the said prediction, since the above species are D0, D5 and D10 which have the CFSC 0. It is also observed that the ions in between them passes through a minima owing to CFSC. We know that lattice energy of a solid increase with decrease in the ionic radius. From this trend in ionic radius, we can predict that the lattice energy for metal oxide will just be an inversion of this graph. The prediction matches with the experimental calculations. If we add an excess amount of hydrochloric acid to COH2 2+, there occurs a color change to blue due to the formation of tetrahedral cobalt chloride. Similar addition to nickel H2 has no effect. This observation is explained by OSSC, octahedral site stabilization energy, defined as the difference in CFSC between the octahedral and tetrahedral geometry. As nickel 2+ has higher OSSC than the cobalt 2+, it is less likely to show octahedral to tetrahedral conversion. There are also many other applications of CFT which I have shown in this slide. Now, it has been found experimentally that when a metal ion gets coordinated with a ligand and forms a complex, the repulsion existing between d electrons of the metal complex become less than that of the metal ion in the free state. This is known as the nepheloxetic effect or the cloud expanding effect. As the CFT doesn't take into account of the metal ligand overlap, it fails to explain the nepheloxetic effect, which is the main limitation of this theory. Here are some other limitations of this theory. This is my reference. Here is my acknowledgement. Thank you.